All right, it's time for us to get started. Just a little reminder. I know it's nice out. I know it's Friday, so it's going to feel like it's more than 50 minutes. It's just 50 minutes. Please give us 50 minutes, okay? All right, so things coming up include the final exam and the optional standardized exam. Very important. If you have a conflict that prevents you from taking the exam with other folks, you need to let me know by Monday, okay? All right. Is there anybody in here that thinks they're in that boat? This is going to be delivered, administered on May 2nd. It's Thursday, starting at 6:30, ending at 8:30. Yeah. What's that? No, they're not. They're not. It is an optional exam, and it's given during Dead Week. And then, no, the final exam is scheduled during finals week, right? It's going to be an exam that I write, and it's going to be cumulative over the course of the semester. So, and if you're registered for this section, you'll take it at 2:15 on Wednesday. If you choose to take the optional exam, then you can take the optional exam on Thursday. And if you like the score, then you can use that as your final. But I'm not mandating that. Okay? Does that make sense? Any questions about that? All right, so things that we've done previously. We've talked about the temperature and the pressure dependence of the Gibbs energy. The first equation listed up there it was basically derived for an ideal gas. The Gibbs energy at any temperature, or at any pressure, is going to be the Gibbs energy at 1 bar plus RT ln pressure, P. All right? And then for the temperature dependence, so basically if we know delta G at one temperature, we can calculate delta G at another temperature as long as we know what delta H of the reaction is. All right? Because that equation that gives us the Gibbs energy at an arbitrary pressure for an ideal gas is an easy-to-use expression, we've decided to take that equation and modify it slightly to permit it to be used for non-ideal gases. And basically what we've done is we've replaced pressure with fugacity. Right? And then from there, we looked at the Gibbs energy as a function of temperature. I like this graph because it shows a little bit more than the graphs that we've seen before. But we know that G equals H minus Ts. And so if I look at G as a function of T, I get 3 different functions that correspond to the different phases. And what we know is the slope of each of these is going to be given by minus S. Right? And then we step back and say, well, we have these 3 different functions. They all give me the Gibbs energy. How do I know what function is going to determine what phase I'm in? Right? And what we know is that systems move in order to minimize their Gibbs energy. Right? And so when I look in this temperature regime, this says that the lowest Gibbs energy possible corresponds with the solid. When I look in this temperature regime, then I'm in the liquid phase. And if I go to higher temperatures, I go into the gas phase. Right? I also wanted to show this one because this is slightly different in the sense that I've still got my 3 functions, but now I'm looking at a temperature, and what I see is that low temperatures, the Gibbs energy tells me I'm in the solid phase, and then at higher temperatures, I don't go into the liquid phase. I'm going directly into the gas phase. Right? So this just helps emphasize the fact that this curve is at a given pressure. This is at a given pressure. All right? And this pressure has to be less than what point on the phase diagram? Not the critical point, the triple point, because the triple point is where you have an equilibrium between the 3 phases. And if you are at a pressure less than that, there's only 2 phases that have minimum Gibbs energies in those regimes. All right? Okay, so we've pointed out that when we're along the coexistence curves on a phase diagram, the Gibbs energy of the 2 phases at equilibrium are identical. Thus, delta G for the phase transition is equal to 0. We already talked about this portion, so we don't need to do it again. We introduced the chemical potential. We're going to be exploring that further today and in the future. For right now, what we need to know is that the chemical potential reflects the change in a Gibbs energy due to changing the number of moles of a component in either a mixture or a reaction. Okay? And we'll be exploring that a little bit today. All right? So one of the things that we're going to see is that the chemical potential of a pure substance is the same as the molar Gibbs energy. All right, so that's going to be important. We'll be covering that. From there, what we're going to do is we're going to derive Clapeyron equation, the Clausius-Clapeyron equation. Who recalls the Clausius-Clapeyron? So that showed up in 178. Not sure. You saw it in Chemie 210. Okay. So we're going to derive this expression today. We might not get all the way through it. All right. The other thing I just wanted to mention, I probably should have talked about this last time. So this is basically to help us understand what vapor pressure is. So if I have a liquid and I put it inside of a closed vessel, what we automatically see happen is some of the liquid molecules or atoms, whatever the liquid's made of, are going to evaporate into the gas phase, right? So this pressure above it is going to be increasing, right? At some point, you're going to reach saturation in the vapor phase. And at that point, the rate of the evaporation is exactly balanced by the rate of condensation, right? So that basically says at this point, you have an equilibrium between the gas phase and the liquid phase. That pressure that's over this liquid is what we call the vapor pressure. It's the equilibrium pressure above a liquid. All right, and then where we ended last time was we looked at two different mini phase diagrams. So I have temperature as a function of pressure in both cases. So on the left side here, what we see is as the pressure goes up, we see that our melting point is also going up, right? Right? And then similarly over here, this is the vaporization temperature or the boiling point. And we see the same relationship. As the pressure goes up, the boiling point goes up. Okay? All right, the other thing I wanted to just mention at the outset is you look at these two curves and you say, well, I'm getting a pretty significant change in these temperatures for change in pressure. I want to just emphasize that the scales are completely different, right? This is 5,000 atmospheres, which is on the order of 4 times 10 to the 6th torr, right? And so what this is saying is, for me to get a small temperature change in the melting point, I have to vastly change the pressure, all right? And we're going to see that down the road a little bit today, all right? So now we look at the phase diagram of water, right? So one of the things I wanted to point out, in this particular case, what we see is that as the pressure goes up, I'm going to roll this down a little bit. All right, so let's say that I'm starting at this point and I increase the pressure holding the temperature constant. Increasing the pressure means I'm trying to compress the system, right? And what I see is that there's a phase transition that occurs that leads me into the water phase, liquid phase, all right? And that tells us something about the density, right? So this says the density of water is related how to the density of ice? It's greater. Okay? So this slope is what determines, is how we can tell what the relative densities are. If I have a positive slope, then if I start in the liquid phase and I increase the pressure, I go into the solid phase. That tells me the solid is denser, right? So we're also going to see that the phase diagram that you've seen previously for water doesn't tell the whole story, right? So we'll see the rest of the story a little bit. Okay? All right. All right, we'll fill in this blank in a moment. All right. What I want to do is take a moment to talk about what happens as a function of temperature to the molar density along the the curve between the triple point and the critical point. All right? So right now we're focused on this portion of the curve. All right? All right, and this is where I want to remind ourselves of what we've seen earlier in the semester. This is another phase diagram. This phase diagram is going to be in terms of pressure and the molar volume, and these curves we've seen are isotherms, right? If my isotherm is at a temperature below the critical temperature, then I've got two phases. That corresponds to my coexistence phase. So at a given temperature, say 13.2 degrees, I've got two phases at equilibrium. Is this going to be the liquid or is this going to be the gas? Well, it's the gas partly because it says G here, all right? But the other thing we know is that this is molar volume, all right? And we expect that the molar volume is going to be greater for the gas phase than it is for the liquid phase. Right? So we can take that same information and write it into a different graphical form. So 1 over the molar volume or the molar density. So I'm going to start with the triple point, T triple. And the last point, the last temperature that I expect to still see any evidence of two phases will be the critical temperature. So T critical. And one of the things that we recognize is that if we're at the critical temperature, we only have a single phase, right? So what's the difference between the gas and the liquid density? There isn't one, right? There's one phase. All right, so starting at that point, I've got a lower trace and an upper trace, right? That mimics this shape, all right? So then I need to identify which curve corresponds to the liquid phase. So what's the upper curve? It's going to be the liquid phase because it's got a larger density or a lower molar volume. So there's my liquid, and there's the gas or the vapor. Okay? All right, so as a critical point is approached, density of liquid and gas approach each other. All right, we also can look at what happens to the enthalpy change on vaporization as we approach the critical point. All right? So where I want to start this is to say, if I'm on the liquid-vapor coexistence curve, I know I have equilibrium between the liquid and the vapor phases. All right? So what's delta G of vaporization? It's equal to 0. All right? And because we know delta G is equal to delta H minus T delta S, this tells me that delta H of vaporization is equal to T times delta S of vaporization at the phase transition. All right? And then I can separate this out and say, well, that delta S corresponds to S of the liquid, or the vapor, minus S of the liquid. Okay? Right? And so it's pretty clear that as I approach the critical point, since I'm becoming one phase, these guys are approaching each other, which means delta H is approaching 0. All right? So as critical point is approached, delta H, delta S are both approaching 0. All right? And that's what this curve shows. Okay? All right, and then at the critical point, we've established that delta H equals delta S equals 0 for this phase transition. Okay? All right, and then I said we were going to see a little bit more about water. Right? So this is a phase diagram that you can see goes to much higher pressures than the previous phase diagram. All right? So this little line here represents the liquid and then the normal everyday ice that we run into, right? And so definitely if I start here and start increasing the pressure, I go from this common ice up into the liquid phase. But if I increase the pressure further, I get into a different solid phase, right? And these different regions all correspond to different crystal structures associated with water, right? And so what we can say at this point is that, if I'm coming along this curve and I end up in ice 5, that's going to be denser than liquid water. And ice 6 is going to be denser still, okay? How many people have heard of ice 9? Nobody? Right. Nobody's read Kurt Vonnegut's books? All right, so I'm not going to go there. All right, this next section is a lot of review. G. How many people have heard of Kurt Vonnegut? A few of you? Okay. Is a function of T. Right? And again, this is review, so we can go through this pretty quickly. We've previously shown that dG dt is the same as negative entropy. All right? And so this is specifically data for benzene. If we're at low temperatures for benzene, it goes into the solid phase. Go to higher temperatures, it's liquid. And then basically we've taken a whole chunk of data out because it didn't show us anything new, and we're just looking around the vaporization point. Right? But what we can conclude is that when we're at 270 Kelvin, we know that the minimum Gibbs energy corresponds to the solid phase. And when I'm at 285, what's the minimum Gibbs energy? It's going to correspond to the liquid. Right? And when I go to high temperatures, I find that it's in the gas phase, right? So this is the same graph that we introduced last time. It's the same graph that we started out with on the first slide. We've just chopped it into 2 different pieces, right? I see that we don't have great enthusiasm here, so we're going to pump sugar into a few of you. Unfortunately, my chocolate supply is a little low, but what can you do? I know I can buy more, but I can't buy it yet. Okay, so now this next part is a little bit new to us. So in this case, we're going to look at the Gibbs dependence upon pressure. So previously we've shown that dG dP is the same as the volume, all right? So we're going to talk about each of these graphs in turn. I do want to put this in with respect to a phase diagram, so I'm just going to draw a generic phase diagram here. I'm going to leave a part off for a moment and it'll become clear why. All right? So what we're looking at here is Gibbs energy. Gibbs energy is a function of pressure. So what distinguishes one from the other is that we're using a different temperature. So at different fixed temperatures. All right? So that basically says that I'm starting, somewhere here, increasing pressure, moving in that direction. Okay? All right, so I start up here for A. I see that at low pressures, I'm in the gas phase. I increase the pressure, and the Gibbs energy crosses over into the solid phase, right? So at this point, I've got equilibrium between the gas and the solid, and then at higher pressures, I'm in the solid region. What can you tell me about the temperature of this system? What's it lower than? All right, so if I started here and I went up, I would go into the liquid phase, right? If I started here and I went up, what phase do I go into? I go into a solid phase, right? So that says that we are at a temperature less than the triple point. Does that make sense? All right, so we come on to graph B. Low pressure, I'm in the gas phase, right? So I'm down the gas phase, and then I come up, and then that point where I start to have other phases with the same Gibbs energy, I see I've got liquid and solid and gas all with the same G. What does that tell me? I'm at the triple point. Okay? Now there's another piece of information that I can glean out of this, right? This also says when I increase the pressure, I go into the solid phase, right? So if I go up beyond this, I'm in the solid phase. What does the slope of the coexistence curve for liquid and solid have to be? Positive or negative? It has to be positive. All right? If these had been flipped, then I know that it would be a negative slope. Okay? All right, and then for C, we see that as we increase the pressure, we start down the gas phase, increase equilibrium between the gas and the liquid. So that tells me that I am greater than the triple point. All right? But it also tells me that I'm below another critical point, right? I don't know why I thought that was humorous. Less than critical temperature, right? Right. And then the last one that we can explore is we look at this and basically we see we increase the pressure, the Gibbs energy is just constantly changing, we have no phase transitions occurring. That tells me that we are at a temperature above the critical temperature, okay? All right, section 9.3, we're going to be talking about chemical potentials of a pure substance in two phases at equilibrium. All right, and what we're going to see is that if we're at equilibrium, the chemical potential of each phase is identical. Okay? All right, so we're going to start by talking about two phases at equilibrium. Where are we? So we can say that the Gibbs energy of our system is given by the Gibbs energy for phase A plus the Gibbs energy for phase B. Right? That should make sense. Okay? And now we're going to say, well, let's let some of my molecules or atoms in phase A move into phase B. Right? That means I'm allowing a change in the number of moles. Right? So when I do that, then I have to say, well, how does that impact my Gibbs energy? All right? And the way that does that is I'm changing the number of moles of A, all right? And what's going to relate dN to dG is dG dN for phase A. I need to hold temperature, pressure, and pressure constant, okay? All right, and yeah.
No, the A doesn't mean to the 8th power.
No, that's a label. That is a label. All right. Okay. And let me just say, I'm trying very hard to be consistent with the labeling in the textbook. I will say that they flip things around a lot, and it's hard. But yes, you are correct. And then we can say for phase B, the change in the Gibbs energy for phase B is going to be given by the change in the number of moles in phase B times dNB. Okay? Now, because I have a pure substance, dNA and dNB are going to be related, right? If something leaves A, it goes into B, right? So that means the change is going to be equal, but the direction is opposite. So dNA equals minus dNB, right? And again, consistent with the textbook, I would not have chosen DNA, right? Because it just confuses you, right? And if I had all power, I would not choose mu for dGdN, right? Because it means like 10 things. All right, but at any rate, we have what we have. All right, so this basically says I can take this DNB and replace it with the negative of DNA. Right? And that's what I'm going to do next. dG, A, dN, A, T and P constant, dG, B, dN, B, T and P constant. I want to multiply this whole thing by dNA, which means I need to put a negative sign here. Okay? Right, so this is where your textbook formally introduces chemical potential. All right, so we can say then that dG for our component, the change in G for one of our components due to a change in the number of moles of the component holding T and P constant, is the same as the chemical potential for that component. Right. So this is where they drop this to a subscript. Right? It's them doing it, not me. Right? So at any rate, what I can do is I can take this chemical potential, replace dG, dN for both A and B. So that's going to get me chemical potential for A minus chemical potential for B times the change in the number of moles of A. Okay? All right, so let's talk a little bit about this. If I want a spontaneous process to be occurring, what's dG have to be? It has to be less than 0. It has to be negative. All right, so let's look at some possibilities. If our chemical potential is greater for phase A than for phase B, this difference is going to be a positive or negative number. It's going to be a positive number. So that becomes positive, right? And for it to be spontaneous, this has to be negative, all right? All right. If dNA is less than 0, that means particles are leaving A and going into B. Okay? All right, so for this example, what we're seeing is my high chemical potential is in phase A, and the spontaneous process is for particles to move from that phase to the lower chemical potential. Right? Then I go to look at the other possibility, or one of the other possibilities. In this case, we're going to say chemical potential for phase B is greater. Right? Well, in that case, this becomes a negative value. All right? And that means that this has to be positive if I want it to be a spontaneous process, right? So dNB is less than 0. And that basically means that particles are moving from phase B to phase A, right? So in both cases, when dG is less than 0, the spontaneous process occurs where I have mass or matter moving from the high chemical potential to the lower chemical potential. Right? And this, of course, explains the reason for calling this potential. Right? The natural direction is to reduce the potential. Right? So it's an analog to electricity. All right? All right, so the final case for us to think about is if we're at equilibrium. Well, if we're at equilibrium, we know that dG is going to be equal to 0, right? And that means that our chemical potentials have to be equal to each other. Right? And so if there's no difference in potential, there's no driving force for matter to move from one phase to the other. All right, so the next thing that we want to do is to show that the chemical potential is the same as the Gibbs molar energy, or G over N. Okay? All right, so that's what our goal is, to show that this is true. All right, so we're going to start. We have this definition. This is our definition. Chemical potentials dG dN. All right? And then what we're going to do is we're going to say, well, let's assume that the Gibbs energy is the chemical potential times N. All right? So I put that in there. All right, so that's my Gibbs energy. I take the derivative of this, and my chemical potential depends on T and P. Right? So this is going to be the derivative of N with respect to N times the chemical potential. So that comes out to be equal to the chemical potential. So this is the thing that we assumed is true. Okay? All right, so we can conclude that G over N is the same as the chemical potential, which is same as the molar Gibbs energy. Okay? All right. We're going to use everything that we've introduced up to this point to determine P and T dependence on a coexistence curve. So basically, we're looking for dP, dt. Okay? All right, so that's our goal. We want an expression for dP dt. All right, and what we can say is that if we have two phases of a pure substance at equilibrium, we can say that the chemical potential for phase A is the same as the chemical potential for phase B. All right? And because we're talking about a pure substance, this is the same thing as saying the molar Gibbs energy for phase A is equal to the molar Gibbs energy for phase B. Okay? And this part should be pretty straightforward. If these are equal to each other, delta G is equal to 0, that's what we mean by equilibrium. Okay? All right. So what I can do then is I can take a total differentiation of both sides of this with respect to T and P, right? Because again, we're looking for dP dt. Right? So we need to know what the dependence is on pressure and temperature. So for the left side, this will become du for phase A dP times dP plus du, and I should be saying mu, dt, holding pressure constant, holding temperature constant. Okay, right? Oops, and that should be A. Sorry about that. Right? So that's the total differential of the left side. I need to do the total differential of the right side. Right? So that will be the partial of mu phase B with respect to P, holding temperature constant times dP, plus the partial of the chemical potential for phase B, changing with respect to temperature, holding the pressure constant times dt. Okay? All right. And then down below, I've done exactly the same thing, but now for the molar Gibbs energy. All right? And so what we can establish is that dP, that means that this is the same as this. This, the same as this. This. They're all identical, right? Okay? All right, so let me just write that explicitly. dG, A, dP, constant temperature, is equal to the change in the chemical potential for phase A due to a change in pressure for T. Okay? All right. So this also gives us a little bit of power because we recognize that we've previously shown dG dP is the same as the volume, right? And because this is molar volume, that's going to be the molar volume of A. And dG dt is the same as minus S, so that's the same as negative S for phase A, all right? dG dP for phase B will be the molar volume for phase B. dG dt will be minus S for phase B. Okay? All right, so I can do those substitutions. All right, so let's do that. All right, so basically we've got VA dt minus SA dt. Whoops, that should be a dP. My apologies. dP minus SA dt. And then on the right side, I've got the molar volume for phase B, dP, minus the entropy, molar entropy for phase B dt. Okay? All right. Again, thinking about what we wanted, dp dt, we're close. That means I need to collect the terms for dp and collect the terms for dt. Okay? So a little bit of algebra. At this point, I can say VA, the molar volume for A, times dp. Molar volume for B, I subtract that from both sides. So that becomes minus VB, molar volume, whole thing multiplied by T dp. Right? And then for entropy, I've got minus S dt on this side. So I'm going to add S for A dt to both sides. So that will get me S phase A minus S phase B dt. Okay? All right. And then I recognize, well, that difference between the molar volumes, that's just going to be the difference between the two phase molar volumes. So I can say this is delta V of the phase transition per mole. This is the entropy of one phase versus the other phase. So that's delta S for the phase transition per mole. All right? So putting that all together, I end up with dp dt is the same as delta S of the phase transition over delta V of the phase transition. All right? So if we knew delta S and delta V of the phase transition, we know the slope. Okay? The other thing that we recognize is previously we've shown at a phase transition delta S is the same as delta H over T. So if I put that substitution in, then I can say that dp dt is the same as delta H of the phase transition over T delta V of the phase transition. Right? And this is the Clapeyron equation. Okay? And it's pretty clear that it gets us the relationship between P and T. Okay? All right, so P versus T, or dP dt. All right? The other thing I want to just mention, for this particular derivation, we didn't need to make any assumptions at all. Everything was equal. We didn't need to assume any particular phases. So that means it works for this coexistence curve, this one, as well as this one. So any phase coexistence. In fact, it would work on a solid-solid phase transition. Okay? All right, well, let's do a little bit of an example of this. So what's the change in pressure needed to increase the freezing point of water by 1 degree Celsius? All right? So basically, we're just going to plug in to that equation. Okay? All right, but before we do that, let me point out, we're looking for the change in the pressure. So I need to rearrange this and say dP is equal to delta H of the phase transition over T of the phase transition, and then delta V of the phase transition, and then times dt. Okay? All right, so the information that we have the delta H. That's good. That's what we need, right? We have molar densities. Well, we don't have molar volumes. What can I do to a molar density to get it to a molar volume? Reciprocal, right? So this turns out to be 0.019, I think it's 1965. And that sticks with me because I was 5 in 1965. Anybody else 5 in 1965? No? Yeah, everybody's thinking, oh my God, he is so old. All right, and if I do the same thing for liquid water, I end up with 0.0180 decimeters cubed per mole, right? And because I'm interested in knowing the difference between the molar volumes, I'm going to calculate that difference. And for this phase transition, delta V and this is fusion, is equal to minus 1.6 times 10 to the minus 3 decimeters cubed per mole, right? And as we've discussed previously, going from the solid to the liquid, we expect that kind of a change, okay? All right, so next up we need to plug in some values, all right? So we can say the integral of dP is going to be delta P, right? And we're asking the question, what's the change in pressure going to be, right? So delta P is what we're interested in, right? And that means I need to take the integral. What we're going to do is we're going to assume that delta H and delta V aren't strongly dependent on temperature. So that's going to allow us to pull that out front. So we've got 6,010 joules per mole. That's our delta H. Delta V, minus 1.6 times 10 to the minus 3 decimeters cubed per mole. I'm going to include the negative sign there, right? And if you think back to this, at this point, we've got the integral of 1 over t dt, right? And what's the integral of 1 over t dt? That's going to be the natural log of the temperature, right? So it's going to be a natural log. And the freezing point of water is 273, and we want to know the pressure change that gets us to 274, right? So this is T2 over T1. Let me just explicitly write that, T2, T1, right? So I left some space in here because we want the pressure in bars, but we have joules, all right? And so what we want to do is to get out of joules. And so what I'm going to do is introduce our conversion factor. We can use R, 8.1314 joules per mole per K. And that's the same as 0.01813 bars decimeters cubed per mole. I should have left a little bit more room there, per Kelvin, right? And at that point, the units all cancel, and our answer is minus 135 bar. All right? So this basically says that if I want to change the melting point from 0 degrees Celsius to 1 degree Celsius, I need to reduce the pressure by a lot. Right? And that's consistent with what we've said previously, that our melting points, fusion temperatures, aren't strongly dependent upon the pressure. Right? So in case it wasn't obvious at this point, dP dt, this is pressure versus temperature, that's the slope of that curve. Okay? All right, and then of course we can ask the other side of this. What's the change in the melting point caused by a change in pressure? Well, that basically means that we're going to look at, by changing the pressure by 1 bar, we'll basically look at dP dt for that relationship. And that turns out to be minus 0.0074 K, right? So really, this tells us, and this is the same process that we've done previously, so I'm not going to go through the calculations again. But what this says is, if I double the atmospheric pressure, we're at about a bar, top about 2 bar, pretty small change. All right? And those of you that have gone to like mountaintops and stuff, you know that changing the pressure causes a big change in the boiling point. Okay? All right, so the other thing I just wanted to mention is, you know, we have an equation here. So this also means that if I know dP dt and delta H and T, I can calculate delta V, right? Or if I have delta V, dP dt, I can calculate delta H, all right? Okay, so in the next section, what we're going to do is introduce the Clausius-Clapeyron equation. All right, and I'm going to start by saying that this is an approximation. How many people that have been exposed to it before know that it's an approximation? Yep, right? And it's in part approximation because we are going to derive it using an ideal gas law. All right, so if we deviate from ideal gas law, that means it's not going to work. Right? So the Clausius-Clapeyron is useful, but this other equation, the Clapeyron equation, is, it's useful under all conditions. All right? Okay, so let's start with the derivation. So what we just showed, the other thing I want to mention before we go forward, because we're talking about a derivation involving the ideal gas law, that means that when we're talking about equilibria, one phase has got to be in the gas phase, right? So this doesn't work for melting points, right? So this would be for sublimation and vaporization. Okay? All right, so what we've just shown is that dP dt is the same as delta H over T and delta V of the phase transition. Okay? All right, so our approximation that we're going to make is we're going to assume that our molar volume of the gas is much greater than the molar volume of the liquid or the solid. All right? And if I make that assumption, then I can get rid of the molar volume of the condensed phase. All right? So at that point, I can say delta H vaporization over T times just the molar volume of the gas. No delta. Okay? All right, next up, we're going to look at dlnP dt. Right? So we know that the derivative of the natural log of x with respect to x is 1 over x. So in this case, this becomes 1 over p dp dt. Okay? All right, so looking forward a little bit, dP dt, dP dt, we're going to be substituting that in. Now we're going to say we know it's an ideal gas, right? Or we're assuming that we have an ideal gas, right? So if I have an ideal gas, 1 over P is going to be the same as RT over the molar volume of the gas, right? So that's 1 over P. Everybody got that? Okay, let me just write up here to be clear. P equals RT over the molar volume of the gas. All right? All right, now I can bring in dP dt times delta H vaporization over T molar volume of the gas. Any possibility of simplifying? I've got the molar volumes to cancel. Right? So those guys go away. And this equals delta H vaporization, turn off, over RT squared. Okay? All right, so let me just write this out. So when I make these notes, I type in the parts I'm planning to write, and then I pull them out to give to you, and sometimes I forget to make up the space. Right? But at any rate, we can say that dlnP dt is the same as delta H of vaporization over RT squared. All right? And we can rearrange this and say dlnP is equal to delta H of vaporization over RT squared dt. Okay? All right, so what I want to do next, assuming I still have time, is to do an indefinite integration of that equation, right? So that's going to get me, on the left side, ln p plus c. On the right side, if I assume that delta H is not strongly dependent on temperature, then I get out front delta H vaporization over R, right? And then the integral of T squared is going to be T to the minus 2. It's going to be minus T to the minus 1, right? 1 over t, negative sign plus a constant. Okay? All right? And what I wanted to just point out here is that if I combine these constants into a single constant on one side, y is a function of 1 over t. If I assume that's x, that's my slope. Okay? So y equals mx plus b. Okay? And that's probably a clean place for us to stop for today. Okay? All right. Have a good weekend. We will see you guys on Monday. Thank you for your attention and patience today. I appreciate that. Enjoy your weekend. If you have not picked up your graded homework 10 or 11, they will be available in the hall in 2 minutes.